A simple elevator is made out of a platform and a rope. The platform starts out motionless and it's going to be raised from ground floor to the 6th floor. Which statements are true about the time when the platform is at rest on the ground? I'll draw several important times in the life of the platform here. One of the times is when it's just resting on ground. Alright, so when the platform is at rest on the ground, the rope that's holding it could totally go slack, so that it's not really being used in any way. And if it's not being used, then something else must be holding this platform up and stopping it from falling toward Earth's center. Because you have your weight of the platform, it's got some mass, so it's heavy. There must be something counteracting that. So what's counteracting it? There's going to be a normal force from the ground that's actually doing the job of holding that platform up and counteracting the weight. But then what can happen is the rope can tighten. We can start to get some tension in that rope, but it doesn't automatically take over the job right away. It could be that it just goes slightly taut, and let's say now there is some tension in it. Alright, so the blue represents the tension due to the rope. The N represents the normal force due to the surface. Even though I drew them kind of angled like that, they're actually both supposed to be pointing straight up. It's just that's how we draw more than one force in, when they're together like that. Okay, then what can happen is the rope can really get tense, and it can take over the job of the normal force completely, where the tension matches the weight of the platform. And at that time, the normal force gets to become zero. There's a balance, so it's like it's about ready to lift off, it's like ready to go. So at the beginning, when the platform is at rest, the acceleration of the platform is zero, hasn't moved yet. The force of gravity acting on the platform may be balanced by a combination of tension force from the cable and a normal force from the ground. That's actually true. That would be seen in picture 2 here. The force of gravity acting on the platform may be balanced by a normal force from the ground alone. That is true as well. We can see that in picture 1. The net force on the platform is zero. That is true in all the pictures. The forces acting on the platform are unbalanced. That's not true. They're balanced. Force of gravity acting on the platform may be balanced with a tension force alone. That is true. All right, so that's that. Now, what about when the platform first begins to move upward? So what'll happen is the tension force needs to exceed the weight in order to accelerate this platform. There's no way it could accelerate if the tension force was staying equal to the weight. We've got to get it to start to move upward. So we need that tension force to be big, at least for a brief transient time, to get the platform moving. So now, according to Newton's second law, according to his first and second law, the forces would not be balanced. Tension force exceeds the weight, so the acceleration now is not equal to zero. We're going to have acceleration. Alright, that's going to cause our platform certainly to lift off the ground. And we can maintain that imbalance of forces as long as we want. We can let the tension stay larger than the weight for a while if that's what we want. And if that happens, then the acceleration is not equal to 0 again. So there's acceleration. So which statements are true about when the platform first begins to move upward? Is the net force on the platform 0? The forces on the platform are balanced? No. The acceleration of the platform is 0. Yeah, so this one's not true. This one's not true. Forces on the platform are not balanced. The acceleration of the platform is 0. That's not true. The force of the cable action on the platform is larger than the force of gravity action on the platform. That's the one that's true. But now it's asking about what happens when your platform is allowed to move upward with constant velocity. So here, when it's on ground, at this time, there's no question that the V is 0. It's not moving. And here, it's not moving. Even here, it isn't moving yet. There's acceleration, but it's still on the ground. But it's going to start increasing its speed. Now, there is velocity. And if you want that velocity to remain constant, what you have to do is you have to stop the acceleration. Acceleration means changing velocity. So how do we stop the acceleration? The answer is you need to lower the force of the tension to get it to again equal the weight. So you bring it down, you lower the tension. And the funny thing is, and what's so counterintuitive, it goes against what people would think. In this case, we have constant velocity. The platform is moving. And what's weird is that this diagram, though, matches this diagram. They're the same diagram, but in one case it's not moving, but in the other case it is. So here, there's velocity. And this shows that the meaning of translational equilibrium doesn't mean you're not moving. See, we have translational equilibrium in this case. Forces are balanced, but you're not moving. But this one also shows translational equilibrium. And as long as you have some velocity, you'll just maintain that velocity with those forces. Alright, hope it makes sense. So the force of the cable action on the platform is equal to the force of gravity action on the platform. That's actually true. The only way we can have constant velocity is if the forces are balanced. The force of the cable action on the platform is larger than the force of gravity. No. The acceleration of the platform is 0. That's true. Forces acting on the platform are balanced. True. And the net force on the platform is 0.